So thank you. Thank you for being here today, and thank you. I'm going to thank you now for hopefully at the end engaging in a discussion about where we think, as a whole, we think renewable energy should go, and what chemistry and what science can do for renewable energy. So I'm going to throw the onus back on you at the end. So renewable energy, energy as a whole. We use energy all the time, do we not? Whether it's to heat our homes. I have to be careful. Sometimes when I'm especially here in London, not so much in Edinburgh, which is where I come from, I'll put the heater on, but here we could put the air conditioning on as well, because of course it's regulating the temperature for how you want to be. We use energy to drive our cars, fly the plane. Industry uses huge amounts of energy, of course. And then where is renewable energy in all this energy mix? How much renewable energy should we be looking at to use here in the UK? So what have you used? What energy have you used today? Well, I'll have a guess. I would guess some form of transport. For me, I took the train down here, and then the tube, and then I walked because it was quite pleasant. But I expect some of you have taken a taxi, some of you probably used a car. I doubt any of you have flown to get here today, but we've all used probably some sort of form of transport. Many of us will have had a shower. I'm not going to say everybody, and I'm not going to ask for who hasn't, but a shower. We've used hot water to have the shower, unless you're a masochist and have had a cold shower this morning. You've used energy to probably cook something today, whether it's toast or a kettle or a cooker or something you'll have used that way. And then, of course, how many of us today could not get through a day without either an iPad or a mobile phone? And here they're twittering away here on the front line with their phones here. So they're using energy as well. So we all use energy all the time. And I could have come up with 100 more examples, but we all use energy throughout our day. I doubt none of you don't use it at some point or another. But the question is, how much energy are each and every one of you and me using throughout our day? Now, we can have a number, but numbers and units, unless you're really familiar with them, don't actually mean very much. So I prefer to think of how many energy slaves are working on my behalf, or how much are working on your behalf every minute of the day. And my energy slave is going to be a person, but it's a man, riding a bike in my garage, and he's generating electricity, generating energy for me to use. So, do I need one person in my garage? Do I need two? Do I need three? How many people do I need? Well, let me give you a wee help here. So, somebody riding a bike, here's me riding a bike. I thought these riding a bike businesses and seeing how much energy you could generate from riding a bike, gosh, I could barely get above a energy-saving light bulb. I think we could all probably do the phone charger at 2 kilometers an hour, but remember, you've got to do 2 kilometers an hour all the time. It's just not a quick burst of 2 kilometers an hour. You've got to do it all the time. But I doubt, even if I was to get a very good cyclist or a very fit sports person, I doubt they could do a flat screen television for any length of time. And yet we all use and all watch a flat screen television all the time. So, having seen numbers like this, how many energy slaves do you think I need? 50. I need 100. I need a big garage. But I would need, and all of us in the West, all of us, particularly in the UK, would all need 100. I mean, if we're talking about the States, for example, they need a lot more than 100, but we would need 100. And when you think about a jumbo jet, it would need 1,600,000 of these people cycling away just to take off. And it would have to move into a major hangar at this stage in time. So you can see that actually we all are very energy hungry, and we use a lot of energy just day to day. Have we always used this much energy? Well, of course, no, we haven't. So if we look historically at our energy consumption, then from when man or woman first became use energy at all, then we've not, for most of the history of mankind and womankind, we haven't really used that much energy. And the energy that we did use was derived from humans, that's slaves rowing the boats or riding the bike in my garage, animals, think about the mules, donkeys walking around to buy windmills and things, for example, fire and wind. Those were the sources of energy. And then what happened? Well, we had the Industrial Revolution. And the Industrial Revolution happened, and we got massive exploitation of fossil fuels, and so our energy usage skyrocketed. Huge exponential growth. And the question is, can this last forever? Can we keep growing? Can we keep consuming energy exponentially the way we have done since the start of the Industrial Revolution? At the moment, where does that energy come from? Well, worldwide, approximately 80% of the energy comes from non-renewables, that is, fossil fuels, oil, coal, and natural gas. 80% of world energy comes from burning fossil fuels. Around about 10% from biomass, 5.7% nuclear, and here where we think of what we would think of as renewables, if I was to ask you what you would come up with renewables, it would be down here. It's a drop in the ocean. Not much at all. Who uses it? Where is this ever-increasing demand for burning fossil fuels coming from? Well, actually, if you look, it's coming from the non-OECD countries. The OECD countries, of which we are one, of course, is not actually growing that much. It's the non-OECD countries, and therein lies some of the discussions that we can have, because, of course, we have a wonderful lifestyle, do we not? We use energy without stopping to think about it. If you want a cup of tea, you go and put the kettle on, because you have access to electricity. You have access to all this energy, so you use it quite often, most often, without thinking about it. But many parts of the world do not have access to that. And who are we to deny them access to energy? And so that's something I think has to be fed into the argument, is how do we make sure that everybody has, everybody aspires to having a wonderful lifestyle. We want to level up. We do not want to level down. You would not take it kindly if we were to say, well, by the way, you can only have half your energy now. You can't, you can't have it the rest of the time. You wouldn't take that kindly. And why should you? So part of the argument, a part of the discussion is how can we level everybody up? And one of the most shocking statistics, I think, is that about 1.6 billion people have no access to electricity. Even today, a seventh of the population does not have access to electricity. We're over here now. So we've used much of the easy gained, easy access fossil fuels. Much of the easy oil we've got, and the gas. So now we're into extreme fossil fuels. We're into deep sea drills. We're into drilling in the Arctic. And fracking. Where does that have its place? All questions that deserve proper airing and proper conversations. Where do these extreme fossil fuels fit into the mix? And how extreme are you prepared to go to add to the fossil fuel demand that there is out there? What's the problem with burning fossil fuels? Well, as many of you know, burning fossil fuels releases CO2. You release carbon dioxide when you burn any of the fossil fuels. Carbon and oxygen, when you burn anything, you have to burn it in oxygen if it's going to burn efficiently. Carbon and oxygen give you carbon dioxide. Now, carbon, is of course coal. Of course, there's a whole lot of impurities and other things in there, but mainly it's carbon. So you are burning straight carbon in oxygen when you burn coal and giving CO2. Methane, CH4, is natural gas, mainly. And if you burn methane in oxygen, you get carbon dioxide and you get water. One fuel that you can burn in oxygen that does not give you carbon dioxide is hydrogen. And we'll come back to at the end again the hydrogen economy, and perhaps we'll discuss about the hydrogen economy and what part that has to play. But hydrogen is a clean fuel. If you burn it, you do not release carbon dioxide. And this is just some of the energy that you can release from burning each of these different sources. And you can see that burning hydrogen is the one that gives you the most energy at the end of the day. And here's the amount of carbon dioxide that's released for burning each of these fossil fuels. And you can see the worst one is coal. Coal gives you the most carbon dioxide per unit of the fuel itself. And what's the problem with carbon dioxide? Well, carbon dioxide is a greenhouse gas. It's not the only greenhouse gas, but it is a greenhouse gas. And greenhouse gases, what they do is that they trap heat in the atmosphere. And so if you increase the amount of carbon dioxide, which is a gas, into the atmosphere, you will result in the Earth becoming warmer. Global warming, climate change. And that's what we're now seeing. I hope that scientists have now convinced the general public that climate change and global warming is a real thing. But if we haven't, I think we have probably persuaded many of the young people who are now taking it up in arms and really getting out there and trying to make people change their minds. So carbon dioxide is a greenhouse gas. We have increased the amount of carbon dioxide into the atmosphere since the Industrial Revolution to heights that has never been seen for many, well, for a long, long time, if ever. So carbon dioxide release when you burn fossil fuels is one of the concerns about burning them, but it's not the only thing. There's the question of energy security. Most of the oil and the gas that we rely on comes from an unstable part of the world. And so energy security is a very real and a very live concern. If you were to consider the time that it's taken to lay down these fossil fuels, coal, oil and gas, and put that and say that the length of time that has been used to produce all these fossil fuels, and say that's a year. then the rate at which we're burning the fossil fuels will have burnt them all in the first 30 seconds of that year. That is how quickly we are burning them in relation to how long it's taken to produce them in the first place. So if we've burnt them all in 30 seconds, what are we doing for the other 365 days of the year, practically? And finally, I'm a chemist. So I think that oil is far too precious to burn. We should be using it as a, well, I mean, we need it as a feedstock. The whole of the plastics industry, for example, relies on oil. If you've burnt it, what are we going to do for a lot of the modern materials which we rely on today? So I think it's far too valuable to burn, and we should be keeping it as a feedstock, particularly for generations to come. So let's look at other energy resources that we might be able to call upon. Now, there's the globe there, up there. There's the world. And that's the diameter of that globe is how much energy we're going to, that's how much energy we need, all right? That's my measure here. So that's how much usage, how much energy we need in 1 year for the globe to function as it currently does. And you can see that if we were to rely solely on uranium, then there is enough uranium around for about the next 30 years, give or take. And remember, of course, once you've got the easy bits of uranium out, it becomes really difficult, just as we were having, as I was saying to you about the drilling for oil and gas. As it becomes more difficult, so uranium will become difficult. Natural gas is around 100 years. Oil's around 100 years. There's masses of coal. There's enough coal to last us for well over 2,000 years. But as I showed you before, coal is the worst culprit for releasing CO2 of all the fossil fuels. So those are the non-renewables. What about renewables? What about potential renewables? And there's our globe again, saying how much we need to use. If we were to use all the ocean tides and currents that were possible to utilize, there is not enough ocean tide and current to satisfy global energy needs. There isn't enough. It can be part of the energy mix, and for countries such as my own, Scotland, then it's going to be one of the major contributions to the energy mix, but it isn't enough for everybody. The same with hydroelectric. The same with wind. There's a lot said about wind, and in this country we're fortunate. Wind is very important, but it isn't the answer for the global energy needs. Geothermal and photosynthesis is, of course, wonderful, but scientists for years have tried to replicate photosynthesis. It's a really complicated thing, and we have got nowhere near it. There has been a lot of work, and I think there should still be a lot of work. But have we cracked photosynthesis? We have not. Have plants cracked photosynthesis? Yes, they have, and well done them. It's a pity they can't speak and tell us how to do it. But of course, solar. That's my research area. Solar, there's masses of solar energy. There's more than enough solar energy out there to help us all, to provide all the energy we'll ever need. It's a difficult sell in Scotland, I'll give you that. But it is part of the energy mix. And solar energy is really, really important. And I'm just going to spend a little time talking about some of these, but mainly about solar. So harvesting wave and tide energy, the sea around Scotland, I'm going to be quite parochial here. The sea around Scotland has the potential to provide about 25% of the EU's estimated total capacity. In other words, the sea around Scotland can produce a huge amount of tidal energy that will be hugely important for the UK and is already hugely important for the UK. And wave power, it's estimated that the waters around Scotland can produce 10% of EU capacity. So we have a real opportunity here to be able to produce significant amounts of energy from renewable sources. And at this point in time, I have to say that Scotland has set itself very, very ambitious targets to be able to meet these renewable energy. So Scotland, just in the last few days, has decided that by 2045, it will supply all of Scotland's energy needs, electricity, heat and transport by 2045 from renewable energy. That is quite an ask. Although I have to say that last year Scotland produced 74% of its electricity from renewable energy. So it's actually doing very well. It's well ahead of its targets, but we have to keep going. And to be perfectly honest, because I will be perfectly honest here, I think we're doing a splendid job, and I will always talk up because the government has really got behind doing this. But we're still digging out or drilling out the oil and gas from the North Sea and shipping it elsewhere. We are still doing that as quickly as we can. And there needs to be, I think, a rebalancing there. So those are the offshore renewable energy, and it's just to say the UK leads the world. Well done us, and let's continue to do that. What about solar, which is what I've had my whole research career in? Well, 1 hour from the sun is more than enough for the whole of the world's energy needs. So you can see we've a lot to play with there. However, sunlight is low energy density. It doesn't, and we need to be able to therefore use solar energy to make electricity and energy cheaply. We need to make it cheaply because it's not particularly focused, the energy. And silicon cells, which is the ones that are currently, that have had the best track record to date by a long way, they're still pricey. So silicon solar cells first came to prominence in the 1950s. And they were so expensive that they could only be used to power satellites, because that was the only way satellites could get any energy. But they were so expensive that that really is the only place they were used. By the 1970s, the price had come down sufficiently that places that couldn't transport through pylons or underground cables electricity, for example, but came from wealthy countries. So, for example, Australia could afford then to have solar energy cells in the outback. So farms could produce electricity from solar cells, but it was still very pricey, and so it wasn't routinely used. By the 1990s, we were seeing it on houses. And now you can see the panels put on the roofs of many, many houses. But I think we can do better than that. So I think what we should be doing is helping construction firms, for example, to build the roof tiles out of solar cells. And then they will just become part of the roof, not a particular eyesore, and will be really useful for that. But I think we have to make it easy for the construction industry, for example, to do that. And you can see, unsurprisingly, I think if we'd all had to plot a graph, we would have plotted a similar graph, as the price of solar energy has come down, so its usage has gone up. I mean, that's basic economics, isn't it? You could have all drawn me that graph. But I don't know that I would have known that the leading solar installers, those that use solar most, is China, then Japan, and then the USA. So solar photovoltaics, that's what I was interested in. Solar cells, dye-sensitized solar cells, I spent my whole research career doing. The silicon cells that we've all grown up with to date are based on semiconductor physics, really. And what you do is you harvest the light, the sunlight, which you then turn into electricity, across the band gap of the semiconductor, and silicon is a great semiconductor. But so is cadmium telluride, and that's as is gallium arsenide. And we can discuss them later if you wish to. These are highly efficient. They have great stability, but they're expensive. And they're expensive because of their production method. You have to produce them in clean rooms. If you get any impurities in there, your efficiency, etc., is shot. Dye-sensitized solar cells, which is the one I was interested in, is when you have a dye molecule that absorbs the light and turns it, and then you put some other components in the system to convert it into electricity. And that's the dye molecule harvests it by a molecule. It might be a metal complex, it might be an organic chromophore, it might be a polymer. Fashions come and go. These are low cost because they're relatively easy to produce. They're lightweight and they're flexible. All good positives, tick, tick, tick. But they're not nearly as stable as the silicon cells, and they will degrade. And they are less efficient. So these two we need to crack before this can overtake that. And I started doing solar energy when I went out to Australia. What better place to do solar energy? Sitting outside, looking, making sure I gathered the sunlight up. It was great. And a dye-sensitive solar cell works as follows. Here's your dye. This is a ruthenium dye that was produced by Gretzel many years ago and is still the marker, is still the one everybody has to beat. It's a ruthenium molecule. Ruthenium is a transition metal. It's not terribly plentiful, so will it ever solve the world's needs? No, it won't, because there's not enough ruthenium. But what happens when you shine light onto this ruthenium molecule is that an electron is excited from the metal, from the ruthenium, onto one of these bipyridyl groups, these double nitrogen groups here. And it's excited onto one of those. That's what happens. And that electron then transfers to your transparent, through your titanium dioxide, through the transparent conducting oxide round and does the work, comes back to the top surface, and then undergoes a redox reaction with your electrolyte to give you back that electron, and that's what happens. So what you need for an efficient, good dye-sensitized solar cell is you need a good dye, you need the titanium dioxide, and you need an electrolyte, and you need some transparent electrodes. Why do they need to be transparent? Because you've got to get the sunlight in. Not much use if we just had two metal electrodes. The sunlight couldn't get in there. So we need to have one of them, has to be transparent. And here's what happens if you want to have the physics drawing of all the energy levels, etc., etc. The D is your dye there, and when you shine the light on the dye, an electron is promoted from the ground state, where it's resting, up to an excited state, D star. And then that electron, the energy level of that excited state of the dye has to match that of the titanium dioxide so that the electron transfers round. And then you get back to the whole transporting material, the triiodide iodide thing I had before, to take the electron back to the donor again. Don't worry, there's not an exam. So what sort of properties do we need in the dye? Well, what we need is we need the dye to have a gap from where the electron is promoted from its ground state to an excited state that matches the solar spectrum. So actually what you want is something very dark green in color. That's why leaves work so well, because the green color matches the solar spectrum so well. So that's just showing you that. we need this dye to strongly bind to the titanium dioxide, because you don't want it drifting off. You need it to be anchored in place to do the work. And that's why we have these acid groups here. This is an acid group here, because that binds to the titanium dioxide surface very strongly. We need, when we shine light and excite this electron, the electron needs to shift position. It needs to move from one part of the molecule to the other part, another part of the molecule, because unless you have that, it'll just fall back down to the ground state again. So you need to physically shift its position. It needs to be very highly colored, because if it's very highly colored, then it will absorb the sunlight much more efficiently, and you can have a really thin cell. So much more efficient. So you need it to be highly, highly colored. Ideally, you want it to be black. And it has to have, the excited state needs to be long-lived enough to do something, whether it's to transfer the electron or to do some chemistry or something, but it needs to be able to stay on there and do something. So we need some charge separation. And Gretzel, as I said, this was given the very catchy name N719. And it's still the dye that everybody measures to. And that's me with a lab-based, not one that's going to solve the world's energy problems at that size, with a solar cell in my hand. And that picture was taken last month as part of a Women in Science exhibition. And that's an exhibition celebrating some of Scotland's finest female scientists. So I would put that up, wouldn't I, because I'm in there. But that's another one of my passions, as you so kindly said, Andy, is about encouraging women to take up STEM subjects, and then having taken them up, to retain them in that and to get them through to senior level positions, to take up leadership positions. And this is the Royal Society of Edinburgh is trying to encourage more women both to take up STEM subjects and then, having taken them up, to keep taking them and to rise to senior positions. And this exhibition has just opened, and I think it's a great exhibition, and everybody who goes into it says it's visually stunning. They did have a very good photographer. But I think what's interesting for me is that there's a lot of interesting stories there about what different science, what different engineering, what different technology and maths that each of the individuals has undertaken. But as somebody said to me the other day, the thing that for them from the exhibition was that everybody had a human story, that everybody was human, and that everybody came to do science and why they did it for very, very different reasons. Thank goodness. But I think that's also the reason we have a problem. If there was one way, then we would have solved it long ago. Anyway, that was my quick diversion just to plug this exhibition. If you're in Edinburgh, go and see it. It's lovely. So back to solar. In Scotland, there's over 1,000 and more coming on stream all the time. There's a lot of live solar farms in the UK. I mean, I got the train down, and I don't know about you, but as you come down in the train and you go through around Peterborough area, God, there's no sheep or anything around there. There's no it's all solar panels, isn't it? It's amazing. And the largest in Scotland is in Perthshire, with sufficient panels for 3,500 homes. Of course, the Americans do it so much bigger than we do. And there we're talking in terms of football pitches. But that's a picture from the desert where the land isn't used for anything else, so why not use it for solar panels? The UK in 2017 actually managed 24 hours without turning on the coal fire stations, which was fantastic. Really pleased. And more days like that have happened in the intervening 2 years. However, where did the energy come from then? Well, it came from gas. Well, that's no good to us either, because that just produces CO2. So although we can be pleased we're not using coal, we're still using gas. and we also imported some. I think that's cheating. Some companies are proud of their renewable energy. And I've taken a Scottish example. Mackey's, who produce ice cream and crisps. What two better food groups are there? And you can see that they use solar, they use turbines, wind, and they purchase some from the grid. But the amount they're purchasing from the grid is decreasing. So some companies do take renewables, and I'm not being paid by Mackey's either. But, you know, I think great encouragement should be given to those that do. The problem with renewable energy is it's intermittent. So the sun doesn't shine 24 hours of the day. Sometimes the wind doesn't blow, although Edinburgh, it's always blowing. But sometimes the wind doesn't blow. The tides are only twice a day. So the question then is, how do you boil your kettle in the middle of the night if you're relying solely, if it's in the middle of the night and it's a calm day? So how do we store this energy? Well, there's many different ways we can store energy, and for as much as people are working on renewable energy, there's as many people working on how to store that energy. So, of course, we can have the lithium battery, which has had a lot of press and is the reason that we all have mobile phones, tablets, and laptop computers, because of the lightweight battery that's in there. And these are all lithium-based. And the lithium battery industry is worth a colossal sum of money. And what happens in a lithium battery is you shuttle lithium plus ions between your anode and your cathode, and it's recyclable, so you can send them back again the other way. And that's just one of the many different types of lithium battery that there are. The problem with lithium batteries is they're great, they're lightweight, fantastic. There is not enough lithium in the Earth's surface for it to solve all our problems. So we can't use, you know, otherwise everybody would go and build enormous amounts of lithium batteries. There's not enough lithium to do that. So lithium batteries are not the complete answer. They're going to be part of the solution, just as solar and wind, for example, are part of the renewable energy mix. So I think energy storage will have different components making it up, and batteries undoubtedly will be one of them. But we do need to look to get more batteries that do not rely on lithium. And sodium batteries are now really getting much more press, but of course they're much heavier. And here are some lithium batteries that are pictures taken from the web in America and in Finland. And you can, you know, they are economically, well, you wouldn't get these ones if it wasn't economic, it didn't make economic sense. So you can make large-scale lithium batteries. Hydro is another way of storing energy. When you've got too much energy, you pump water uphill. When you need energy, you put the water downhill. You let it flow with gravity downhill again. And this is at Cruachan in Scotland, in the north of Scotland. It was built in the 50s, when much of the hydro schemes were actually built in the UK. And in those days, it's built, the scheme is inside the mountain. So it doesn't disturb anybody's beautiful views of the lochs there. There's your feeder loch at the top, where the water comes down from. Sorry? Is that right? So the water comes down from there, and then when you've got too much energy, you can take it from the major loch down at the bottom and take it up the top. I think the wonderful thing about that, two wonderful things. One, it's inside the mountain, and if any of you have been to it, it's just really impressive. You can drive in and it's just incredible, all this technology inside the mountain. And the other thing is that once the water comes down there, turns the blades to make your electricity, they then have to slow that water down, because they can't let that fast-flowing water come into the loch, because it'll disturb the environment, the local environment. And they do that so well that there's a fish farm directly opposite that hydroelectric scheme. And that is, for me, the best example of showing how well they've slowed that water down so it makes no difference to the local ecology. And we have, these are just showing some of the energy systems. We can have pumped hydro, where the water's pumped uphill and released when you need to produce electricity. And it's very good if you're watching your football match and the halftime comes and everybody wants to go and make a cup of tea, because you can turn these hydroelectric schemes on and they will instantaneously produce the electricity that you need to meet that demand. So they're very good for meeting peak demand when you know there's going to be a peak demand. But I'm a chemist, and of course, where's the easiest to store energy? It's in a chemical bond. Chemical bonds all have energy associated with them. So why, as chemists, would we not store our energy in a chemical bond? And there's whole swathes of research done on ammonia, so known as the ammonia economy. Ammonia is made advantages. It's much easier to transport than many things. So there's the ammonia economy. There's the hydrogen economy. We have a real research endeavour in, however, storing that hydrogen we produce. But remember, right from the word go, if you burn hydrogen, you simply produce water, so you're not adding to greenhouse gases. And finally, why would you not use CO2 itself? The bond energy in CO2 is incredibly high. It's a thermodynamic sink for carbon is carbon dioxide. But why can we not use renewable energy, such as sunlight, to break that CO bond? We'd have to get some catalysts in there, etc., and get some good chemistry involved. But if renewable energy was cheap, we could break that CO bond easily. We could then gather up all the CO2, she says easily, gather up the CO2 and use it to produce fuels like ethanol, which you could then use to run cars with. So we could have CO2, and I think that is part of the energy storage solution. And a lot of people are doing some research on that. So I'm leaving you with that slide of some of the challenges for global energy, and you can read that yourself. But I hope I've given you some ideas of the challenges, some of the concerns that we have, and I just put it to you is, how can we make this revolution really, really happen so that we leave this world in a great place for our descendants to come? So thank you very much indeed.